till now we have seen the functioning of current transformer, the basic operating principle of the current transformer, and the difference between the current transformer and a normal transformer. We have also seen how to calculate various errors and other terms related to the classification of current transformers. In one of the lectures, we have also seen how to classify the current transformers based on the IEEE standard as well as the IEC standard. Now today we will discuss a very small topic of the polarity of the current transformer and some connections, particular connections of the current transformer. We will also see what are auxiliary current transformers. Before going on to that topic, let us see some very brief points which are usually seen practically in current transformers. As we have seen that there are CTs which are called bushing CTs, which are placed inside the bushings of an equipment like that of circuit breaker or usually a transformer bushing. Okay, so due to the putting of the current transformer core onto the bushing, the mean dia, like this is the bushing and the core is wound here like this, and here secondary is wound like this. Okay, so according to the bushing size, due to the insulation requirement, this mean length will increase. Okay, so the bushing CT will have more magnetic material as compared to other normal CTs available in the market or for similar purposes. Okay, so because of this, what happens in bushing CTs? Since L as well as the other dimension is also kept large, so the cross section, if we see the cross section of the core, we will find that the flux has more surface area to pass through. Okay, so there will be lesser possibility of saturation in a bushing CT at higher current levels. So we can say that bushing CTs are more accurate than other CTs at higher currents. However, at lower currents, because the magnetic material is high and we still need some minimum level of magnetization, so there will be a level of magnetizing current which should be required by the CT. So at lower current levels, this magnetizing current will be in higher proportion to that of the actual current. So the accuracy of bushing CT is little bit inferior at lower currents, but these are very accurate at higher currents. Okay, so this is the first point. Now nowadays we see that overcurrent relays or other relays are not electromechanical type. They utilize digital or numerical technology. We will see the construction of various relays in one of the subsequent lectures. So in the old type relays, we can see that to operate they would have required minimum number of ampere turns. Okay, so this I pickup for usual normal old type of overcurrent relay would be inversely proportional to the number of turns tapped by the relay or tapped in the relay, because if this is, let us say, is fixed to produce some kind of motion, so if I either increase this or increase this, the effect will be similar. So we can say that I pickup is inversely proportional to the number of turns tapped. Okay, now we also know that the inductance of any coil is proportional to the number of turns squared. So in all type relays, we could see that the inductance of the coil of the relay is inversely proportional to the I pickup squared. So accordingly, the burden of the relays used to get changed with the I pickup or the number of turns tapped. Okay, so in older times this was a little bit difficulty in the designing of the CTs. Okay, now we have seen the terminology of burden of a CT. Usually burden is either defined through the burden impedance or the volt ampere rating connected to the secondary of the current transformer. With power factor usually it is given. Okay, now we have seen that this VA or ZB is usually calculated only for the single current transformer and the burden connected to it. Okay, so this is one transformer and this is the burden, and the calculations were easy. Now let us assume a case in which two CTs are connected in series on the secondary side. Let us say this is the primary, this is first CT and this is second CT. Okay, and we are connecting a burden in this series. Now let us say this voltage across this CT is V1 and across this CT is V2, and the current circulating is, let us say, I. Okay, so what will be the burden of the CT? Now this is little bit different for because we have not given the definition of burden in similar situation. Okay, so how to calculate the burden on each CT? It is very simple. We will find that the burden on each CT will be simply the voltage across its secondary and the current through its secondary. So for this CT, for CT1, the burden will be V1 over I, and for CT2, the burden will be V2 over I. Now in the next slide we will see what is the benefit of such kind of connection. That is, we are connecting two CTs secondary in series with the burden. That we will see in the next slide. Now let us take a scenario in which the power system is not that much large, that is, the currents flowing in the power system are not that much large. Okay, so the current, let us say, flowing in the power system for my example is just 40 ampere in the primary side. However, let us say the nearest available CT is 50:5. Okay, the 5 ampere rated secondary. So the turns ratio will be simply 1:10. Now for such small turns ratio, the CTs will not be having enough burden rating. Okay, however, the relays have some specific burden rating, so the number of relays is quite similar to every power system. Okay, so the burden capacity of CT will be undersized according to the requirement. How to cater for this problem? How to solve this problem of undersizing of CT as compared to the burden required to be put on that CT? Let us see. Let us say that I have a CT and over it a burden is placed. Okay, let us say the voltage across the CT is V and the current is I. Okay, now we can see that the burden seen by the CT as of now is V over I. Okay, now this V over I, the burden seen by the CT is higher than the capacity of the CT, because the CT is a very smaller turns ratio CT. Its magnetic material is not that enough available, so it cannot sustain this much of burden. So how to resolve this? What we will do, we will take similar CT, same kind of CT, so that we have matching characteristics of the CT, and we will put it like this, and we will connect their secondaries in series. Now since these CTs are same, so the voltage induced will be same and the current will be I. Okay, now this burden ZB, what it is equal to? It is equal to the voltage across burden, which is 2V, over the current I. Okay, now the burden total is 2V over I, ZB. Earlier this ZB was equal to V over I. Okay. However, what burden this CT will see? One CT will see. According to the definition which I have told in the previous slide, the burden seen by the CT will be the voltage or the potential difference on its secondary and the current flowing through its secondary. Now the voltage across the secondary of one CT is V and the current flowing is I. So the burden is simply ZB over 2. So you can see now that we have halved or reduced the burden seen by the CT by a factor of 1 by 2. Okay. So in this way we can solve the problem of node matching or the undersizing of the CT as compared to the burden capacity required in the power system. Okay. Now there is one issue with this kind of thing. What is that issue? Let us say there is a fault here between the primaries. Okay. So this current, let us say, goes to 100 ampere and this current is 60 ampere in the fault and this current is 40 ampere. Okay. Now this series connection can only have same current flowing through them. Okay. So let us say this current I is flowing through them and this I is being decided by this 40. So 40 over 10 is 4 ampere. So 4 ampere will be flowing. So because of this, what will happen? The remaining 60 ampere current, 100 minus 40, the remaining 60 ampere current which is flowing into the fault will be completely utilized in the magnetization of the core of this CT. So this CT might go into saturation, or if it does not go into saturation, will lead to induction of a very high voltage across this CT. So what will happen? We will require some kind of voltage suppressor or surge suppressor connected across the CTs to avoid such kind of issues because of the fault between the primaries of these two CTs. Okay. Now similarly, these over voltages usually occur when we have capacitor banks. During switching of capacitor banks, usually harmonics are involved in the waveform. Okay, so the voltage induced, the harmonic voltage induced causes peaks in the voltages, or the over voltages are created, and these over voltages can be seen in the CTs also. So these capacitor banks, if these are installed near CTs, then CT insulation rating should be designed keeping this thing in mind, that switching of capacitor banks might require a higher insulation level for the CT also. Now in the next slide we will see what are the polarity system or the convention for the current transformer and what are auxiliary current transformers. Now let us see the polarity convention of the CTs. It is similar to normal conventional transformer. That is, if I show the polarity markings through the dot convention, I will put a dot on the primary, which is just this single wire. I will also put a dot on the secondary. Okay. Now current entering into the dot in one of the winding will require a positive current will be equivalent to saying that current is leaving this dot in the other winding. Okay. Similarly, the potential drop from dotted to undotted terminal is having same polarity. Okay. So this is the sign convention for current transformers. Now let us see what are auxiliary CTs. Now usually what happens, let us say this is a power system with some current rating, let us say some 600 or 1200 amperes, that we will see later. Okay. Now let us say we are using differential protection for the protection of this bus bar. Let us say it is a bus bar. We are putting two CTs and due to difference in ratings available, or maybe due to some difference in characteristics, let us say the turns ratio are not equal for these two transformers. Let us say it is having 500:5 and this is having 600:5. Okay, and let us say the current flowing during the fault is, let us say, 1200 amperes through the primary. Now I am assuming that this fault is a through fault, that is, fault is not occurring between the two CTs, that is, the differential protection should not get activated. Okay, however, due to difference in the turns ratios, what will happen? This CT, the 500:5 CT is going to give how much current? 1200 into 5 over 500 or 12 amps. Okay, and this, how much it will give? 1200 or 5 over 600, that is 10 ampere. Okay, so any relay connected between them will see a spill current of 2 ampere flowing. So you can see that this 12 amp will be like this, 10 ampere here, 12 ampere here. So this 2 ampere will be a spillover current which might activate the differential relay which is being used for protection. So how to resolve this problem? What we will do, we will use a CT that will have a turns ratio. Let us say I will put a CT here, and what it will do, it will be having a turns ratio such that this 10 ampere is reflected as 12 ampere. Okay, so what will be the turns ratio of this CT? It will be 12:10 or 1.2:1. Okay, so in this way, what I can achieve, I will achieve 0 ampere spillover current because 12 ampere will go here directly. Okay, so in this way we can connect an auxiliary CT which is having required transformation ratio. Okay, but issue with this kind of arrangement is that, let us see what will be the impedance seen by this primary CT. Instead of the auxiliary CT, what will be the this impedance seen by the primary CT? What will happen? Let us say any impedance Z which is seen at the secondary terminals of these auxiliary CTs will be reflected according to this turns ratio. So you can see that the impedance reflected towards the primary CT will be higher. So the burden on this CT will increase. Because of this, the errors will be higher in this CT compared to this CT where there is no auxiliary CT connected. However, you can see that this burden impedance can also get reduced depending upon the turns ratio. If the turns ratio was, let us say, 10:12 and the situation was different, then we could have seen that the reflected impedance would have been reduced. However, usually we find that whenever these auxiliary CTs are used, the reflected impedance gets higher on the primary CT which is there, and the errors increase in the primary CT. Now, this concept we have seen for the auxiliary CTs. This is usually used whenever we have some problems of matching of the characteristics of the CTs, usually in the bus protection system or the differential protection used in bus protection, transformer protection. That we will see when we will study these kind of protections. So usually the specifications in the tenders floated by various utilities clearly specify that there will be no requirement of auxiliary CTs in the bus protection to avoid such kind of phenomena of increased error due to auxiliary CTs. Now in the next slide, we will see various kinds of connections of current transformers, and we will try to analyze them numerically or analytically. Now let us try to analyze various kinds of connection of the burden on the secondaries of the CTs for three-phase system. As we can see, usually in three-phase there can be two kinds of connections. One is the star connection and other is the delta connection. Now in the delta connection there can be two variants. The second variant I will draw in the next slide. Now let us first try to analyze these two connections. This one here is the star connection. In this, what we have done, that this is phase A conductor, this is phase B conductor, and this is phase C conductor. The current IA is flowing, the capital A is flowing in the primary, the capital IB is flowing in the second primary of phase B, and capital IC is flowing in the primary of phase C CT. Okay, now these CTs, CT1, CT2, CT3 for phase A, phase B and phase C respectively are connected star on this side. Similarly, the relays for phase A, phase B and phase C are also connected in star on the other side of the CT. So you can see that we have star connection on this side as well as star connection on this side, and these two stars are being connected through a ground relay or the ground fault relay. Now let us see the analytical part of this kind of connection. You can see that this relay RA will see a current IA, which will be just the transformed version of I capital A according to the transformation ratio. Okay. Similarly, IB seen by this relay B, RB will be IB, which will be again transformed version of capital IB. Similarly, the current seen by the relay RC will be the transformed version of capital IC. Okay. So these relays will be called phase relays, will see the current in each phase according to the transformation ratio. Now, what will be the current seen by this relay? Let us see. This relay will see current IA plus IB plus IC. Now this is simply equal to 3 times of I0 or the zero sequence current. Okay, so this relay will see any zero sequence current which will be present in the 3 phases. Okay, so usually this zero sequence current is present whenever there is a ground fault or the fault involving ground is there. Okay, so this relay will act as ground fault relay. We will study this kind of connection in detail when we will study the phase fault protection and the ground fault protection. Here we have just discussed the connection part of the CT for Y connection or the star connection. Now let us come to the delta connection. In the right side, I have shown a delta connection. Now, capital IA current is flowing in this primary conductor of phase A, capital IB is flowing in the primary conductor of phase B, and capital IC is flowing in the primary conductor of phase C. This CT1, CT2 and CT3 are connected in delta. However, the burdens on them have been connected in the star. Okay, now let us see what are the currents seen by these burdens or the relays connected to the CT. Okay, now you can see that if this is IA, this is IB and this is IC, similarly you can see that IA will be a transformed version of IA only according to the turns ratio. IB will be a transformed version of IB, capital B, according to the transformation ratio, and IC will also be transformed version of capital IC. This proportionally constant is equal to the transformation ratio. Okay. Now the current in this branch will be IA minus of IB, because this current is IB. So according to KCL, IA minus IB will be equal to this current. Similarly, this will be IB minus IC, and this current will be IC minus IA. Now let us analyze these currents in terms of phase sequence components or various sequence components. Let us see. Now as we know that IA can be written as IA0 plus IA1 plus IA2. IB can be written as IA0 plus A square IA1 plus A IA2. And IC can be written as IA0 plus A IA1 plus A square IA2. Now we can see that IA minus IB can be simply written as IA minus IB. This IA0 will get cancelled out. IA1 will be common here. It will be 1 minus A squared plus IA2 1 minus A. So you see that these relays will not be able to see the zero sequence current, which is usually there whenever ground is involved in the fault. So these relays or these burdens will act as phase relay only. Okay. Similarly, I can find IB minus IC also equal to IA1 1 minus A plus IA2 IB minus IC. It is A square minus A and A minus A squared. Similarly, this IC minus IA will be equal to IA1 is common, A minus 1 plus IA2 A square minus 1. Now I will simplify this term containing 1 minus A square and 1 minus A in the next slide. We will write them in the complex form. Okay. Now here I have drawn or written the simplified or the complex form of IA minus IB, where 1 minus A square has been written as 3 by 2 plus J root 3 by 2, and IA2 into 1 minus A has been written as 3 by 2 minus J root 3 by 2 IA2, just by using the identity that 1 minus A square is equal to 3 by 2 plus J root 3 by 2 and 1 minus A is equal to 3 by 2 minus J root 3 by 2. Now for balance conditions, we know that IA2 will be equal to 0 equal to IA0. Only the positive sequence current will be present. So this term will be absent. Okay. Now on simplifying, we can see that this IA minus IB is nothing but, if I take root 3 by 2 common or just root 3 common, it is root 3 by 2 plus J 1 by 2 IA1. Now what is this? It is root 3 IA1 angle 30 degree cos 30 plus J sin 30. So you see that the current flowing in the burden is having a magnitude which is root 3 times higher and having a phase angle difference of 30 degree. Okay, that we can easily see because the delta currents are always root 3 times of the currents available here. Okay, in a delta, these currents are root 3 times of the line current. Okay, or sorry, the current flowing in the delta. This is the line current and this is the current flowing in the delta. Now in our one of the beginning of the course videos, we have seen that for a delta, this identity is actually true. Okay, so you see that we will have to give particular importance or particular attention to the difference in the magnitude as well as the phase in the delta connection of CT. Now let us analyze this situation when there is this line to ground fault. Now what will happen in line to ground fault? IA1 is equal to IA2 is equal to IA0. Now let us say if I have provided a path to the flow of zero sequence current, only then current will flow through these burdens, otherwise there will not be any fault current flowing through the burdens. Okay, let us say I have given a path here to, this is the R0, and here I have connected to the star connection. I am giving a star connection also, or this is the ground connection. Okay, now this current will be I0 in this R0, and this relation will be holding for line to ground fault. Now we can see that the current seen by the relay in the phase will be three by 2 minus j root 3 by 2 IA1. Okay, so on solving, what I will see that I have replaced IA2 by IA1 using this identity for line to ground fault. So you can see that IA minus IB will be, in this case, this will be get cancelled out, 3 times of IA1. This gets cancelled out. Okay, so this identity we will see which is simply equal to 3 times of IA0. That is, if I give a path to the flow of zero sequence current, then these burdens will see the zero sequence current during the line to ground fault. Okay, now let us see a scenario when there is double line to ground fault, or let us say just double line fault, line to line fault on phase B and C. For that case, we will see that IA1 is equal to minus of IA2. So what will happen in that case? In that case, this minus sign will come here and this will be replaced by IA1. And instead of these getting cancelled out, this part will be cancelled out, and I will write IA minus IB will be equal to j root 3 IA1 or root 3 IA1 angle 90 degree. So again, the current seen by this relay will be different than the current flowing in the primary side of the deltas. Okay, so in this way we should see that we have to give proper attention to the currents in the various relays flowing according to the connection of the CTs. Okay, now here on the left side I have drawn the different kind of delta connection of the CT secondaries. Now it is an exercise to you to prove that the current flowing in these burdens RA, RB and RC is just opposite of the current which was flowing in these burdens of RA, RB and RC of this connection. It is very easy to prove, and I hope it will be easily proved by the students who have watched my lectures on this course. Now in the next slide we will try to see a very small concept of zero sequence shunt connection in current transformers. Now let us see the very important but small concept of zero sequence shunt connection of current transformers. Now in the previous connections we have seen that the star side of all the burdens was connected to ground through zero sequence relay. Okay, now we will see in our later lectures that we require that the phase relay and the zero sequence relay or the ground relay have the inputs from different instrument transformers due to various requirements. Okay, according to kind of polarization phenomena or something else that we will see in detail in our later lectures. But let us see what is the use of zero sequence shunt connection. Now what I have done here, I have shown three phase conductors, phase A, phase B and phase C. These are CT1, CT2, CT3. These are connected in star. Okay. And here I have connected phase relays. Now since this star connection is not grounded, so there will be no zero sequence current flowing from these phase relays. Okay, so these relays will just act according to the current value of the phase currents of IA, IB and IC, and there will be no zero sequence current. What I have done here, I have taken tap off points from here. These tap off points will take zero sequence component from the current flowing here. Okay, there will be no zero sequence current component here. However, this component will come here, since in the primary side of this CT, I have connected in star and I have connected a burden R0 or the ground relay and connected it to the ground. On the secondary side, to allow the flow of zero sequence currents, what I have done, I have connected the secondary in the delta. So this is star delta connection of the CT, and here it is only star connection of the burden, and this point is not grounded. So ultimately what I have done here, I have separated the zero sequence component of current and the non-zero sequence component of the currents in these three phase conductors. Okay, so, and this kind of connection will be utilized when we will study ground fault relay and the phase fault relay. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.